Hello, students. I hope you all are doing good. So, our today's topic is alternating current NCRT section 7.6 to 7.6.2. So, let's begin. This is a disclaimer. So, after this lecture, you will be able to analyze AC behavior in LCR circuits, including voltage current relationships, phasor diagrams, and resonance application like radio tuners. Okay. So, now in this lecture, in previous three lectures we have discussed about purely resistive circuit, purely inductive circuit, and purely capacitive circuit separately. Now we will do LCR circuit, in which all the three components are in series and attached with connected with external AC source. Okay, now we will see what is the voltage current relationship when all the components are connected in the circuit, and phasor diagrams and their resonance application. So, index of topics. So, NCRT section 7.6, AC voltage applied to a series LCR circuit. NCRT section 7.6.1, phasor diagram solution. And NCRT section 7.6.2, resonance. So, let's start with series LCR circuit. So, consider a series circuit with an inductor L, a capacitor C, and resistor R. All the three components are now connected to an AC source having voltage. Now, we will take the instantaneous voltage expression same as we have taken in the previous three lectures, for purely resistive, for purely inductive, and for purely capacitive circuits. And same voltage source we are going to take in the LCR circuit also. Okay, so this is the diagrammatic representation. So resistance are this capacitor C and inductor L. They are connected in series with the voltage source having instantaneous voltage V equal to Vm sin omega t. So figure 7.10, a series LCR circuit connected to an AC source. Okay, so at any instant, suppose current is flowing in the clockwise direction. Means this terminal of this AC source at any instant is positive, and the lower terminal of this AC source is negative at any instant. Okay, so current is flowing clockwise. That's why here positive, here negative. This plate of capacitor is positive, this is negative, and here positive, negative. Okay, so current is flowing clockwise, and we are also moving clockwise. So let Q be the charge on the capacitor, and I be the current in the circuit at time t. So current will be flowing through resistor and inductor. But in the case of capacitor, we will uh, we will write that Q will be the charge on the capacitor. Okay, we will not specify the capacitive component with the current. Okay, we will specify this component with the charge only. So let Q be the charge on the capacitor and I be the current in the circuit at time t. Okay, so from Kirchhoff loop rule, because voltage across this capacitor will be represented in the form of charge, and voltage across both these components R and L will be represented in the form of current. That's why we have to specify the charge on the capacitor Q. So from Kirchhoff's loop rule, so these steps are same, only expressions are different. So step is same. Initially, we are going to apply the Kirchhoff loop rule in the this closed path. Then we have to find the expression for current. Then we have to find the expression for IRMS current. Then we have to find the instantaneous power, average power, and then phase relation. Okay, steps are same for all type of circuits. Okay, so from Kirchhoff loop rule, sum of potential drop in a closed loop is zero. That is, now move in clockwise direction. Now this voltage source, you are moving from negative to positive at any instant. So voltage, any instantaneous voltage across this voltage source is V. Now you have reached this resistance. You are moving from positive to negative. So voltage drop across this resistor will be taken negative. So minus IR. Now you have reached this capacitor. You are moving from positive to negative. Okay. So voltage drop across this capacitor will be taken as negative. That is minus Q by C. Q is equal to CV. So V is equal to voltage drop across this capacitor will be equal to Q by C and negative. Now across this inductor, so inductor will oppose the change in the current. So EMF will be induced such that it will oppose the cause which is producing it. That's why EMF is taken as with negative polarity according to Lenz's law. So what is the EMF expression which is related to inductance L? It is E equal to minus L di by dt. We have discussed in the inductive circuit also. We have discussed it in the electromagnetic induction chapter also. Okay. So minus L di by dt, which is equal to 0. So voltage drops or gains across the closed path is equal to 0 according to Kirchhoff's loop rule. Okay, so putting V equal to Vm sin omega t in this expression, so it will become IR. So we will shift this all these three terms IR minus Q by C minus L di by dt in the right side hand side, and it will become positive. IR plus Q by C plus L di by dt equal to, and V will remain on the one side of the equation. So it will become Vm sin omega t. So after rearranging this equation, we will we came up to this expression. So it is 7.20. Okay. So finding the solution for voltage and current in series LCR circuit. So IR plus Q by C plus L di by dt Vm sin omega t 7.20 equation. Now, this is the required equation to find the I, which is current in the circuit. So we will solve it using phasor. Now you can see this is a very complex equation. In the case of separate circuits, resistive, inductive or capacitive, equation was simple. We differentiated it, or in the case of inductor and resistor, we integrated it to find the current. Okay, that was simple equations. Now equation is complex. Okay, so we have to solve it using the phasor diagram method. So this is somewhat different from we have done in the all three lectures. This is phasor diagram solution is somewhat different. Okay, but it is done by the phasor, so it is more easy. So again figure 7.10. Now from figure 7.10, capacitor, inductor and resistor are in series. Okay, therefore AC current in each element is the same at an instant. We know that current in the series is same. Okay, so current flowing through series, or we can say AC current or RMS value or peak value, anything. So AC current in each element is same at an instant. So AC current flowing through this circuit will be same at an instant, having the same amplitude and phase. Okay, so AC current will be having same amplitude and same phase across all the components because they are connected in series. So we know in the DC current, when we have taken DC current in the current electricity, we know that in series current remains same. Now in the AC current also, in the case of AC current also, at any time, current will be having same amplitude and phase across all the components because they are connected in series. Okay, so let it be I equal to Im sin omega t plus phi. So you can assume that I is equal to Im, which is its amplitude, sin omega t and phi. This phi. Now this phi is not pi by 2. In the case of purely capacitive circuit, it was pi by 2. In the case of purely inductive circuit, it was minus pi by 2. But in the case of LCR circuit, where effect of all the three components are there, this phi is not fixed. It depends on values of L, C and R. Okay. So let's suppose current is equal to Im sin omega t plus phi, and we have to determine this phi. Mark it as 7.21 equation. So where phi is the phase difference between voltage across the source and current in the circuit. Okay. So this phi is the phase between voltage and current in the circuit. So voltage we have to find. Now we know that voltage drop across all the elements will be different. So we have to find the net voltage drop. Okay, by phasor diagram solution. So phasors VR, VL, VC. So what are these phasors? VR. This is the voltage phasor across resistor. This is voltage phasor across inductor. This is voltage phasor across capacitor. Okay. So you can see figure 7.11a relation between phasors VL, VR, VC and I. So current is having same amplitude and phase across all the components. So it is shown by this I. Okay. Now this VR is shown by an arrow. Okay. So these two arrow, one is for current, one is for VR. Okay. So we know that in the case of resistive circuit, now we are going to use the concept of separate circuit that we have a pure circuit we have discussed in the previous lectures. So now this blue phasor is representing the current phasor. Now VR, that is the voltage phasor across R. We know that for resistive circuit, voltage phasor and current phasor are in phase with each other. There is zero phase difference between voltage and current in the case of purely resistive circuit. So VR, voltage across a resistor, will be along the current phasor. So this VR phasor will be along the current phasor. There is no phase difference in the case of across the resistor. Okay. In case of capacitor, now in case of capacitor, in capacitor current leads voltage by pi by 2, or we can say voltage lags behind pi by 2. So current is in like this pi omega t plus pi. So this VC is lagging behind this current by pi by 2. In the case of inductor, current lags behind and voltage leads. So for inductor, VL is in this direction and it is ahead by current phasor by pi by 2 angle. Okay, we are using the concept of this pure circuit to draw this phasor diagram for LCR circuit. Okay, so let the current phasor be I as given by equation 7.21. I equal to Im sin omega t plus phi. So this is I. Let voltage across the resistor R, inductor L and capacitor C are represented by phasors VR, VL and VC. So voltage across all the components R, L and C are VR, VL and VC respectively. Okay, as I've already discussed. So from equation 7.3, Vm equal to IMR. Okay, so amplitude of the phasor VR can be written as VRM. So amplitude of this phasor VR can be represented as VRM. Okay, which is equal to Im into R. Okay, this is the maximum voltage, or we can say amplitude of voltage across resistor, which is equal to IMR. Okay, from equation 7.14, Vm is equal to IMXL. Now in the case of inductor, now amplitude of phasor VL can be written as VLM equal to IMXL. So in the case of inductor, what is the amplitude of voltage? Is equal to amplitude of current multiplied by inductive reactance according to equation 7.14. Now amplitude of phasor VL, in this case we can write it as, so VL is the voltage phasor of potential drop across the inductor. Okay, so VLM will be equal to IMXL. See, similar for capacitor. So for from equation 7.18, Vm is equal to IMXC. So in the case of capacitive circuit, amplitude of voltage is across the capacitor is equal to amplitude of current in the circuit multiplied by capacitive reactance. So in this case, for phasor VC, that is the phasor for voltage across capacitor, can be written as VCM equal to IMXC. Okay, so notation you should remember. We are going to use it in the further derivation also. So VRM is equal to IMR, VLM is equal to IMXL, and VCM is equal to IMXC. This is equation 7.22. So let at some time t phase of current is omega t plus phi. Okay, so at any time the phase of the current is, in this case, I equal to Im sin omega t plus phi. So phase of the current is omega t plus phi as shown in the figure 7.11a. Okay, as shown in the figure. At any time, phase of this current will be omega t plus phi. Now voltage across resistor is in phase with the current. We know that for a resistor, Okay, voltage across resistor will be in the phase with current. There will be no phase difference between voltage across resistor and current, as we have discussed in the purely resistive circuit. So phasor VR is in phase with I phasor, current phasor. So voltage across inductor is ahead by pi by 2 from current. Now in the case of inductor, we have discussed that voltage leads current by pi by 2 phase difference. Okay, so voltage across inductor is ahead by pi by 2 from current, like shown in the figure. So current is like that, and we measure the angle in the anti-clockwise direction. So from here, from current phasor, it is pi by 2 phase. There is a phase difference of pi by 2 between VL and I. So VL is ahead by pi by 2 from current. Now phasor VL is ahead from I by pi by 2. Okay, as shown in the figure. Now we also learned that voltage lags current by pi by 2 across capacitor. Okay, so this VC, in the case of purely capacitive circuit, we have discussed that voltage across capacitor always lags behind by pi by 2 phase difference with respect to this current phasor. Okay, so voltage lags current by pi by 2 across the resistor. So phasor VC is behind the phasor I by pi by 2, like this. So VL is ahead by current by pi by 2, and VC lags behind current by pi by 2. So they are exactly opposite to each other, VL and VC. And VR is in phase with the current. Total voltage will be the sum of three voltage across resistor, inductor, and capacitor. Okay, so this is the instantaneous values. So instantaneous value at any instant, if we calculate the voltage, it will be the sum of voltage across resistor at that instant plus sum of plus voltage across inductor at that instant plus voltage across capacitor at that instant. So these are all instantaneous values. So if we want to calculate the instantaneous voltage across all the component, it will be the sum of instantaneous values of voltages across all the components individually. Okay, so mark it as 7.23 equation. But this value we have to, these are vectors, so we have to do the vector sum. Okay, so this is for instantaneous value 7.23. But if we want to find the RMS value or peak value, so phasor relationship whose vertical components gives above equation is V equal to VR plus VL plus VC. So if we want to find the VRMS value across all the components, or VRMS value across the circuit, in the circuit, and VRMS value of voltage across all the components, so we have to do the vector sum, because these phasors are vectors. Phasors are rotating vectors. So to find the net voltage, we have, because there is phase difference between all the voltages. So between VR and VL, there is a phase difference of pi by 2. Between VR and VC, phase difference of pi by 2. Between VL and VC, phase difference of pi. So we have to do the vector sum. So V net voltage in the circuit is equal to VR plus VL plus VC. Mark it as 7.24 equation. So this situation is represented in figure 7.11a. So we have to do the vector sum. We cannot add up the voltages directly. These are instantaneous values. In the 7.23 equation, these are instantaneous value. They can be added up simply. But if we want to find the RMS value, we cannot add it simply. Okay. Now B part. Relation between phasor VL, VR and VL plus C. What is VL plus C? For the series LCR circuit. Now VL was in the direction opposite to the VC. So they are exactly opposite. We can add it or subtract it. So we have taken the vector sum of both these vectors, and we have taken these vectors along one direction, VC plus VL. If VC is greater than VL, then they will be in this direction as shown in the B section of the diagram 7.11. If VL is greater than VC, then VC plus VL will be in the opposite direction as that of shown in the B part. So at any instant, VC and VL are always along the same line. Okay, they are exactly opposite or along the same line and in the opposite direction. They can be combined into single phasor. So they can be combined into single phasor VC plus VL, as I have already mentioned that they can be combined. But if VC is greater than VL, it will be same as shown in the figure. But if VL is greater than VC, then it will be exactly in the opposite direction to that of shown in the figure. This situation is represented in figure 7.11b. Okay, since VC and VL are in opposite direction, so amplitude of phasor VC plus VL can be written as VCM minus VL magnitude. Okay, so this is the vector form VC plus VL, but we are subtracting it actually. Okay, we are subtracting their maximum values. This is vector representation. We have combined them. We have applied positive sign. Okay, but this VL is actual. In actual, this VL is in negative direction because VL is represented exactly opposite, like in the A diagram. You can see VL is exactly opposite to VC. So if we want to subtract it from VC and represent in the form of one vector, so this VL will be in the negative. But this is vector representation. We have combined it VC plus VL. Now, when we are going to find the amplitude of this phasor, we will represent it in this form: VCM minus VLM. This VCM is the amplitude of voltage across capacitor, and this VLM is amplitude of voltage across inductor. So we have taken negative sign. So this VLM will be negative because we have taken it in the opposite direction. And we are applying mod. Okay, this is the amplitude of this VC plus VL phasor. Okay, because either VC can be greater, either VLM can be greater. Okay, so we don't know which one is greater. It is based on their properties, their specification. Okay, that's why mod is applied. Now resultant of VR and VC plus VL. So their resultant now VC plus VL in this direction and VR is in this direction. The angle between VC plus VL and VR is 90 degree. So we have to find the resultant by vector addition. Okay, so by the parallelogram law. Okay, so let resultant of phasor VR and VC plus VL be V. So this is the resultant of both these vectors, and amplitude will be VM. So amplitude of this V is final resultant voltage is VM. From figure 7.11b, phasor VR is perpendicular to phasor VC plus VL. Then resultant of two perpendicular vectors is written as Vm square plus V square Rm plus, now amplitude of this VR is VRM. Amplitude of this VC plus VL is VCM minus VLM. Okay, we have to take the square of both these vectors amplitude. So magnitude of this VR is VRM and magnitude of this VC plus VL is VCM minus VL. Okay, we are taking square, so no need to put the mod sign because when we going to square it, it will become positive value. Okay, now there will also be 2AB cos theta, means 2 VRM VC minus VLM into cos theta, but theta is 90 degree here, so that term is eliminated because cos 90 degrees 0, so that term is eliminated. So this is the resultant according to parallelogram law, or we can say triangle law of vector addition, to find the resultant. So finding current amplitude in series LCR circuit, so Vm square equal to Vrm square plus Vcm minus Vlm square. Now putting Vrm equal to Imr and Vlm equal to Imxl and Vcm equal to Imxc. So Vm square will become Imr square plus Imxc minus Imxl whole square. So taking Im square as constant, common out of all these terms, so Im square in bracket R square plus Xc minus XL whole square. Okay, so Im will become Vm upon after rearranging this equation, Im will become Vm upon root r square plus xc minus xl square. So mark it as 7.25a equation. This is the expression for current. The equation gives the amplitude of the current, Im. Okay, we have reached the amplitude of current. Now impedance in the series LCR circuit. So this is the equation. We have derived Im equal to Vm upon root r square plus xc minus xl square, 7.25a equation. Now by analogy to the resistance in the circuit, now we'll draw the analogy like we have done in inductive circuit and capacitive circuit. So in resistive circuit, Im equal to Vm upon r. So this term, this whole term, r square plus xc minus xl whole square and root, this term plays the role of resistance. Okay, from 7.25a equation, we define impedance. So this term is known as impedance of the circuit. Okay, so z equal to root r square plus xc minus xl square, marked as 7.26 equation. So this is the impedance. It will play same role as resistance. Okay, it is analogous to resistor in the pure resistive circuit. So I am equal to Vm upon Z. This is like Ohm's law for an AC circuit. So according to Ohm's law, I am equal to Vm upon R. Okay. So now we have derived the expression and taking analogous, we have reached to the conclusion that Z, this impedance, is equal to R square plus Xc minus XL square root. So now this is like Ohm's law for an AC circuit. Using Im equal to root 2 IRMS and Vm equal to root 2 VRMS, now we will write this expression in the terms of RMS values. So IRMS equal to VRMS upon Z. Now what is the definition of impedance? Impedance is the total effective opposition. So what was inductive reactance? It was the opposition offered by inductor. What was the capacitive reactance? It was opposition offered by the capacitor. What was the resistance? It is the opposition offered to the flow of current by resistor. Now, what is impedance? It is due to the all three components. So impedance is total effective opposition offered by the LCR circuit by all the components to the flow of alternating current. Its SI unit is same as resistance, that is ohm. So impedance diagram. So we'll draw the impedance diagram, a right angle triangle with base R and perpendicular XC minus XL and hypotenuse Z. Okay. So this is phi. In phase diagram, it is shown what is phi. Okay. So this is phi, this is resistance, this is XC minus XL. And this is impedance. So this is called impedance diagram. Okay. So if current is in this phase, current is represented along the x-axis. Okay, so VR will be represented in this x-axis, along x-axis. Okay, XC minus XL will be represented in the perpendicular direction because phase difference between current and this XC minus XL is pi by 2. Okay, we have seen means VC minus VLM, and we have after putting the value of VCM, VLM and VRM, we have came to conclusion that what is VRM is equal to IM R. So after eliminating IM, it is the impedance diagram. So this is represented by R, base is represented by R, this is XC minus XL, and this hypotenuse will represent impedance diagram. Impedance. So we'll calculate the impedance from here. So what is phase angle? To find the phase difference between phasor I and V, we need to find the angle between these phasors. Okay, phasor I is always parallel to phasor VR. Okay, hence it is sufficient to find the angle between phasor VR and V. Okay, so this hypotenuse is representing the this hypotenuse is along the voltage phasor, the net voltage V, and this R is along the VR phasor, voltage across resistance, and this XC minus XL is along the VC plus VL. VC plus VL phasor that we have calculated by combining VC and VL. Okay, from there this impedance diagram came. From that diagram, from the phasor diagram, that impedance diagram is extracted. Okay, so phasor I is always parallel to phasor VR. Hence, it is sufficient to find the angle between phasor VR and V. So this is phasor, this is along phasor VR, and this hypotenuse is along phasor V. So this is angle phi. So we can find the phi now. Like this. Okay, this is phi. This is VC minus VM. This is VRM, and this is V. Okay, so this is V is along hypotenuse. This VRM is base, and this VC minus VLM. This is perpendicular. Okay, now this V will be equal to, this V is having amplitude Vm equal to Imz. This Vc minus Vm, Vcm minus Vlm having amplitude Vc minus, this is, these are having amplitude Vc minus Vcm minus Vlm will be equal to Im Xc minus XL. Okay, and this Vrm is having amplitude Im into R. Okay, so Im will be cancelled out from all the terms. So it will become like impedance. Okay, so after taking Pythagoras theorem, so that's why they are represented in the terms of their impedance. Okay, in the impedance diagram. So let the phase difference phi between phasor VR and V. Now from the phasor diagram, tan phi will be equal to VCM minus VLM upon VRM, which is equal to what is like this, that I was telling you in this diagram. This is represented in this expression. So VCM we can write Im Xc, and VLM we can write Im XL, upon VRM we can write Im R. Okay, and V we can write Im Z. Okay, so that's why this Im will get cancelled out. Okay, so tan phi will be represented in the form of Xc minus XL upon R. By this concept, impedance diagram is represented by only only by the resistance and reactances and impedance, not by voltages like this. Okay, because Im will get cancelled out when we take tan phi or cos phi or sin phi. Okay, so this tan phi is equal to Xc minus XL upon R. Mark it as 7.27 equation. Okay, so this is important expression to find the this phi angle, phase difference of current and voltage. So let's see the phase relationship. Tan phi is equal to Xc minus XL upon R. Mark it as 7.27 equation. This is graphically represented as, so this is impedance diagram again. Okay, so that's why it is represented in the form of reactances, the difference of reactances, resistance and impedance. Okay, if Xc is greater than XL, okay, these are some special cases. If Xc is greater than XL, then phi is positive. Okay, so phi will be in like this, phi is positive. If Xc is less than XL, so this difference will be negative. So this perpendicular will be in the downward direction. So this phi will be calculated as negative. So phase difference will be negative. So phi is positive. The current is predominantly capacitive. If Xc is greater than XL, we can say this is capacitive circuit. Not purely capacitive circuit, but it is predominantly capacitive circuit. Okay. What is the dominant component? A capacitor. Because Xc is greater than XL. So it is capacitive circuit. This LCR circuit is capacitive. Means capacitive reactance is more. Okay. So the circuit is predominantly capacitive and current leads the voltage. But not by pi by 2, some phase angle phi. But if XL will be greater than XC, then phi will be negative, because this term XC minus XL will become negative. So this perpendicular will go in the downward direction, and this phi will become negative. Then we can say circuit is predominantly inductive and current lags the voltage, because it is predominantly inductive. So in inductive circuit, current lags the voltage by pi by 2. But in this LCR circuit, it will not lag behind pi by 2, because capacitor component is also there. Okay, which will reduce the angle. So current lags behind the voltage, but by pi angle, pi phase difference, not pi by 2. It will be less than pi by 2. Okay. Now phasor V and I and their phase differences. Now this is the phase diagram for LCR circuit. Okay. So this is voltage phasor. This is current phasor. So current phasor is having phase omega t plus phi, as we have seen. I will was equal to I am sin omega t plus phi. Okay. So at any instant t1, current is having phase omega t1 plus phi, and voltage is having phase omega t1. Okay. So phase difference between voltage and current is phi at any time. Okay. Now this is graphical representation. So current is leading. So it is condition basically based on XC and XL. If XC is greater than XL, then current will lead by phi angle. If XL is greater than XC, then current will lag behind. Current will be somewhat here. It will be lagging behind by phi angle, phi phase difference. Okay, according to that graphical representation vary. So in this case, it is taken, it is leading. Current is leading. So current is leading, that means now 0 is starting from 0 of voltage, and maximum value is reached at pi by 2. Okay, but maximum value of current is reached at some another angle, some another phase difference, and for voltage it is pi by 2. Now the phase between current maximum value and voltage maximum value is phi. Okay, and we can calculate the phi if we know the value of XC and XL and R. Okay, now it is not pi by 2 phase difference, it is somewhat phi, it is less than pi by 2. Okay, so figure 7.13 shows the phasor diagram and variation of V and I with omega t for the case XC greater than XL. So we have taken XC greater than XL for this case. You can take XL greater than XC, then phasor diagram will somewhat change, but concept remains same. If we look at the values of current and voltage in figure 7.13a, at time t equal to 0, then current is non-zero, but voltage is 0. Okay, so you can see at time t equal to 0, voltage is 0, but current is having some value, not maximum value, not minimum value, had some another value, because phase angle is not pi by 2 or not minus pi by 2. That's why it is having some other value. Okay, this shows that voltage lags behind the current when XC is greater than XL. If XL is greater than XC, then voltage will lead. If XC is greater than XL, then voltage will lag. Okay. Thus, we have obtained the amplitude and phase of current for an LCR series circuit using the technique of phasors. But this method of analyzing AC circuits suffer from certain disadvantages. So what are disadvantages? Let's see. So first, phasor diagram say nothing about initial condition. Okay, at initial condition, what was the voltage? What was the current? It say nothing about the initial condition. Okay, we take an arbitrary value of t, say t1 as done throughout this chapter, and draw different phasors. We take any arbitrary value. We don't take consider initial condition, that where current was, where phasor diagram was in the initially, where current phasor was initially. Okay, we only take some at arbitrary time t1. Okay, which and draw different phasor which show the relative angle between different phases. But we didn't say anything about the initial condition. Solution so obtained is called steady state solution. Okay, I have discussed that in inductor and capacitor. when we tap the key, when we close the circuit, current will start from 0 to its maximum value. Okay, or in the case of capacitor start charging from 0 to maximum value, and it will take some micro or milliseconds. Okay, during that time interval in capacitor, current will decrease until it is fully charged, and in inductor, current will increase. Okay, initially inductor will oppose the change in current, but after some time, when change in the current becomes 0, then current will be steady in the. So that interval of time where current is increasing or decreasing in the capacitor, that is known as transient time. Okay, we only obtain the steady state solution when current is steady. Okay, but when current is increasing and decreasing, that solution is not obtained by this phasor diagram solution. So there exists another solution called transient state solution. So transient state solution is also there when current was increasing or decreasing across the capacitor or inductor, which is solution at time equal to t positive, zero positive. Zero positive means just very small amount of time above zero. It is negligible. It is nearly zero, but zero positive. So general solution is the sum of transient solution and steady state solution. What is general solution? It is sum of transient and steady state. Steady state is when current is constant, and transient solution is when current is not steady across the circuit. It is increasing or decreasing. Okay, but transient solution time when there was current decreasing or increasing, capacitor is charging, or current was increasing in the inductor. So that time is very, very small. So transients over a long time of period. So after a sufficient long time, effect of transient solution die. When a steady current is established in the circuit, okay, after a certain amount of time, which is very, very short time, okay, so transient solution die out, and behavior of the circuit is described by the state solution. That's why we neglect the transient solution. Okay, but it is not 100% accurate solution because it is not taking into account the transient state solution. Okay, so phasor solution is only steady state solution. We are assuming current is steady in the circuit from the time equal to t equal to 0. Okay, so what is the phenomenon of resonance? So phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. Okay, you may have discussed resonance in the oscillation. Okay, what is resonance? Matching of frequency with some material which is having its natural frequency. So we are matching the external frequency we are giving with the natural frequency of some material, and due to which that material is start oscillating with high frequency than its natural frequency. That is called resonance. Okay, so phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. So AC current is alternating current. Okay, it is alternating after a certain interval of time, after a certain period of time. Okay, so it is have some frequency. If we are giving external frequency and matching its frequency, due to which it start oscillating with the high frequency, then we can say resonance is reached. Okay, so if such a system is driven by an energy source at a frequency near its natural frequency, if we are deriving this, uh, if there is a system having a particular natural frequency, we are deriving that system uh, by the energy source, external energy source, and that external no energy source is having frequency near to the natural frequency or same as natural frequency, then amplitude of the oscillation is found to be large. A familiar example of phenomenon is child on a swing. Okay, so what this is analogous to easily explain the phenomenon of resonance. So swing has a natural frequency of swinging back and forth like a pendulum. Okay, initially we have pushed the swing. Now swing is having natural frequency of swinging back and forth like a pendulum. Okay, but a child sitting on the swing, what he is doing when it start oscillating in one direction, it start pushing it in same direction. just when it is oscillating. Okay, it is at extreme position. Now it just going to start, or it is just going to go towards the mean position. So child is pushing the swing at the same time. So child is pushing the swing at the same time when it is just about to going towards the mean position. So frequency of child pushing this swing and natural frequency of this swing is matching. So amplitude of the swing will increase. So if the child pulls on the rope at regular intervals and frequency of the pulls, so it is pulling the rope at the regular interval and frequency of these pulls is almost same as the frequency of the swinging. The amplitude of the swinging will be large. Okay, that is called resonance. Similar kind of things happen in case of AC circuits. When circuit is driven by its natural frequency, then current flows in the circuit, reaches its maximum value, and power transfer from source to circuit element is maximum. Okay, so what is resonance? Resonance is a phenomenon in a series LCR circuit where current amplitude becomes maximum at a particular frequency. Okay, this happens when a capacitive reactance XC become equal to inductive reactance. Okay, this is figure 7.10 again. Let's try to understand. Consider an LCR circuit in series. Okay. So from equation 7.25a, amplitude of the current is given by Im equal to Vm upon Z, which is equal to Vm upon R square plus Xc minus XL whole square. Okay. So in the resonance frequency, the external source frequency is matching with the system frequency, due to which the amplitude of current will increase. Okay, that means amount of current will increase. How it will increase? When Z will decrease. How Z will decrease? What is the condition when Z is minimum? So Z is minimum when XC become equal to XL and difference between XC and XL becomes 0. So at this condition, Z will impedance will become minimum and impedance will become equal to R resistance and current will be maximum in the circuit. So that is the condition for resonance. So current amplitude Im is maximum when Z is minimum. This occurs when XC minus XL equal to 0. So current amplitude at this condition will be Im equal to Vm upon R. So Z will become equal to R because Xc minus XL will become 0. Here condition for resonance is XL equal to Xc, means capacitive reactance will be equal to inductive reactance. This gives condition for resonant frequency in the LCR circuit as omega naught L. So we have to compare XL equal to Xc. So what is XL? Omega L. So we are at resonant frequency. The frequency at resonance is called resonant frequency. So this is the frequency when XL equal to Xc. So we are writing omega naught here. That is resonant frequency. So omega naught L will be equal to omega naught C at resonance. So we will find the omega naught. Omega naught will be 1 by root LC. Mark it as 7.28 equation. This is the expression for resonant frequency. So omega naught is angular resonant frequency in radians per second. Using tan phi, which is equal to Xc minus XL upon R at resonant, tan phi is equal to 0. Why tan phi is equal to 0? Because Xc is equal to XL and tan phi equal to 0. That means phi is also 0. That means circuit start behave like a purely resistive circuit because phase angle becomes 0. Okay. So at resonance, impedance becomes minimum, which is equal to R resistance. Current becomes maximum and circuit will behave like pure resistive circuit. Okay. So phi will become 0. Hence, at condition of resonance, circuit behaves like a purely resistive circuit, that is Z equal to R, and phase difference between will be 0 between current and voltage phase. Okay. So this is the diagram. You can see figure 7.14. Okay. So figure 7.14 shows the variation of Im with omega in series LCR circuit with L equal to 1 millihenry, C equal to 1 nanofarad for two values of R equal to 100 and R equal to 200. Okay. So you can see at a particular frequency omega naught, current is maximum. The current these curves are showing peaks at resonant frequency. Okay, and you can see when resistance is 100 ohm, the sharpness of this peak is more as compared to resistance is 200 ohm. So sharpness of this curve depends upon the resistance of the circuit. Okay, if resistance is less, the sharpness of this curve will be more. Okay, if we examine this graph of maximum amplitude Im versus frequency omega, then amplitude of current is maximum at resonant frequency, whereas at other frequency it decreases. So to attain maximum value of current in series LCR circuit, resonant frequency plays a very important role. So what is the applications of resonance? So resonant circuits have a variety of applications. For example, in the tuning mechanism of a radio for a TV set. Okay, how we tune the radio? We rotate some button. Okay, to tune the radio for a particular channel, or by the help of remote we change the channel. So what how resonant circuits have a variety of applications. So here is the application of the resonance in the tuning mechanism of radio or TV set. So the antenna of radio accepts signal for many broadcasting stations. Okay, there are so much broadcasting stations and so much channels. Okay, so antenna is receiving every signal. So how we will tune it? So signals picked up in the antenna act as a source in the tuning circuit of the radio. So the circuit can be driven at many frequencies. So circuit can be driven means any frequency can be used to derive the circuit. But which frequency we will use? We will use frequency which is matching with the natural frequency of the radio set. Okay. So but to hear one particular radio station, we will tune the radio. We will set the frequency that this frequency, the channel of this frequency we are going to listen. Okay. So but to hear one particular radio station, we need to tune the radio. In tuning, we vary the capacitance of a capacitor in the tuning circuit such that resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. So we are changing the frequency with the help of some mechanism. We are rotating a button like component. Okay, so we are rotating it, setting the frequency that of this frequency we are going to shift to this channel of this frequency. So antenna is receiving all type of frequencies, so we are tuning it. So in tuning, we vary the capacitance of the capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. Resonant frequency is that frequency we are setting by changing the capacitance. Okay, by changing the capacitance, we are uh, coming up to the resonance condition where Xc become equal to XL. Okay, we are reaching the resonant frequency, and by changing capacitance, we are setting up resonant frequency, and when this resonant frequency become equal to the frequency of the radio signal received, any radio signal received, this channel will appear to start. Okay, so when this happens, the amplitude of the current in the circuit is maximum with the frequency of the signal of the particular radio station. In simple words, we vary resonant frequency of the circuit using capacitor to match with the particular radio station frequency. Okay, so we vary resonant frequency by changing the capacitance. Okay, to match the particular radio station frequency so that resonant condition happen and current will become maximum and we will tune that channel. When the frequency match, we get the clearest and strongest reception of the station signal. Okay, so we will change the capacitance, we will vary the resonant frequency, and then we will start to hear that channel. Okay, so we get the clearest and stronger reception of the station signal, which frequency is matched with the resonant frequency. So condition for resonance, it is important to note that resonance phenomenon is exhibited by a circuit only if both L and R are present in the circuit. Okay, only then voltage across L and C cancel each other, both being out of phase by 180 degree, and the current amplitude is Vm upon R. Okay, so both L and C should be present. At resonant, all voltage appear across resistance. If any of the component will be missing, then XL will not be cancelled by XC. Okay, then resonant condition will never happen. Okay, so at resonant, all voltage appear across the resistor. This means we cannot have resonance in RL or RC circuit. So this is summary. In series LCR combination, voltage phasor across different components have specific phase relationships. VR is in phase with current. VL leads the current by pi by 2. VC lags current by pi by 2. And the circuit's impedance Z is given by Z equal to R square plus XC minus XL square. Where R is resistance, X is capacitive reactance, XL is inductive reactance. The current amplitude in the circuit follows Ohm's law for AC, that is I am equal to Vm upon Z. Phase difference phi between voltage and current is given by tan phi equal to Xc minus XL upon R. The circuit behavior depends on the relative values of Xc and XL. When Xc is greater than XL, current leads the voltage. When XL is greater than Xc, then current lags the voltage. When XL is equal to Xc, this is the condition for resonance. So resonance in series LCR circuit occurs when inductive reactance XL equals capacitive reactance, resulting in the maximum current amplitude. Resonant frequency is given by omega naught, which is equal to 1 by root LC. At resonance, the circuit behaves purely resistively, Z equal to R, with zero phase difference between current and voltage. Resonance is crucial in radio, TV tuning circuits and can have only occur when both L and C components are present. There are some practice question. If in an LCR circuit, XL equal to 30 ohm, XC is equal to 20 ohm, and R equal to 40 ohm, calculate the impedance Z. In a series LCR circuit, if voltage amplitude is 100 volt and impedance is 50 ohm, what is the current amplitude? If the current phase angle phi in an LCR circuit is plus 37 degree and R equal to 4 ohm, calculate XC minus XL. For a series LCR circuit with VRMS equal to 220 volt and Z equal to 110 ohm, find IRMS. In a series LCR circuit with L equal to 2 Henry and C equal to 8 microfarad, calculate the resonant frequency. And a series LCR circuit has a resonant frequency of 1000 Hz. If the inductance is 0.2 Henry, calculate the required capacitance for resonance. So this is all about today's lecture. Thank you.